We ended the last section, 7.2, on sets. We were talking about the number of elements in a set and counting numbers of elements. So we'll continue on with that theme here with 7.3, basic counting principles, and we'll keep counting things and establishing basic counting principles that we'll need when we start really delving into probability. So the first is the addition principle, and it says that the number of elements in the union of two sets, A union B, is the number of elements in A plus the number of elements in B minus the number of elements in their intersection. And that might not seem too intuitive until you think about what's actually happening there, right? So if I have, maybe I should have drawn this a little bit bigger, but if I have A and I have B, and I want the number of elements in their union, well, what happens if you add the number of elements in A? So I take all the elements in A, I add all those up, and then I add to that all of the elements in B. Well, now I throw in all of these guys. Notice what's happening is I'm double counting the intersection, right? When I take everything in A plus everything in B, the intersection region gets double counted. So this is why we subtract it off at the end. So it's the number of elements in A plus the number of elements in B minus the number of elements in the intersection to subtract off one of those cases where we double counted it. And that will leave you with just everything actually in the union in both sets. Right? So because of this overlap region, I have to count it off to make sure it's not double counted. So here is the famous addition principle for sets. And we'll just do a really quick example. Suppose something like, suppose that we've got two sets here. Number of elements in A is 60, number of elements in B is 40, and the number of elements in their union is 80. How many elements are in their intersection? Well, if we use the addition principle, I know that the number of elements in the union, which I have, is 80. Number of elements in the union is going to be the number of elements in each set. So 60 plus 40 minus the number of elements in the intersection, which is what I'm looking for. So all I have to do now is solve for the number of elements in the intersection. Number of elements in the intersection is 60 plus 40 minus 80, which is 100 minus 80, or 20. Alright, so this formula here relates sort of all of the most important aspects of the number of elements in set. It relates the number of elements in the sets individually, and in their unions, and in their intersections. So it's just a nice formula that relates all four of these numbers together. And if you know three of them, then you can always find the fourth. So this problem here is similar to what we ended the last section 7.2 on. We were doing something very similar to this. And I have a Venn diagram. I want to fill in the number of elements in each region and using some of the information we're given. So we're told the number of elements in A is 100, the number of elements in set B is 90, the number of elements in their intersection is 50, and the number of elements in the universe is, in the universal set, is 200. So there's actually one piece of information I can fill in right now. I know directly we're given the number of elements in the intersection is 50. So I know right here in the intersection of these two sets is 50. Now what else can I do? Well, the number of elements in set A is 100. Right? So here I have X, some unknown number of elements, right? Maybe I'll just put a question mark. Some unknown number of elements, but I know that in total in set A there's 100 elements, right? So something plus 50 has to give me 100. So what should be here? Should be 50 elements, right? That means in total, in all of set A, I have 100 elements. Right, so I'm not writing anything down, just I want to go through the intuitive understanding of this, which is I think is important to have. And how about set B? Again, what number should be here? How many elements are in B but not in the intersection? Well, there's 90 total elements in B. We've already accounted for 50 of them, so there must be 40 more in B that aren't in the intersection, because 50 plus 40 is 90. And there's only one more region. That's 1, 2, 3. There's only one more region in here, which is everything outside of both sets. Well, how many elements do we have so far? We've accounted for 140 of them. We know in the total universe there's 200 elements. So if there's 140 in here, there must be 60 more out here, because 140 plus 60 gives us 200 total elements. And that's all there is to it. So you should have this intuitive understanding of, okay, if I know there's 100 elements in A, and I've already accounted for 50 in the intersection, then there must be 50 more outside. And so I haven't written anything down, I haven't written down the calculations that we're doing, but if you have this intuitive understanding, these problems aren't particularly difficult. Here we have another problem, so it's a word problem this time. A survey of 100 people shows that in the past month, 65 people have streamed TV, 45 people have watched cable TV, and 30 people have done both. So a series of questions. How many people have streamed TV but not watched cable TV? How many people have watched cable TV but not streamed TV? And how many people have done neither? So it turns out this is really exactly the same as the last problem we did, just with some words thrown in behind it to give interpretations to these things. But let's see, let's let S be number of streamers, or people who watch stream TV, number of people who stream. Oops, not number, sorry. Let S be the set of people who stream, and let's let C be the set of people who watch cable TV. We'll just say who cable. Apparently cable is a verb now. So we've got a set of people who stream TV, set of people who watch cable TV, and if I build a Venn diagram, we have some people who stream, some people who watch cable TV, and of course there's an overlap between them. And we're told, the survey tells us that 30 people have done both. So I know that I've got 30 people in my overlap. Okay, so what is this asking for? First question is, how many people have streamed TV but not watched cable TV? So the first question is asking, how many people live in here? How many people live in S but not in the intersection? How many people live in S but not in C? Well, this is exactly what we did in the last problem, right? So I know 65 people have streamed TV, right? So in S in total, there should be 65. I already have 30 accounted for, so out here, I must have 35 more. So answer is 35. Part B, how many people watch cable TV but not stream TV? So that's asking how many people live in here, how many people are in C but not in S. So we have 45 people watch cable TV. So if we should have 45 people in total in C and 30 already accounted for, then there must be 15 here. So answer is 15. And last but not least, how many people have done neither? So that's asking how many people are out here in the universe that aren't already accounted for in one of these sets, right? How many people don't stream or watch cable TV? Well, we surveyed 100 people total, so our universe consists of 100 people, and we've already accounted for 35 plus 15 is 50, plus 30 is 80 people. So if we've already accounted for 80 and we surveyed 100, then there must be 20 more people outside there that don't watch TV at all, or watch TV some other way. So there would be 20 people there. So this problem really is exactly the same as the last one, just you have to interpret everything using a Venn diagram. And I highly recommend doing this, right? When you're trying to figure out how many people are in different regions of sets, draw a Venn diagram. They are extremely, extremely helpful. Next up, we've got the multiplication principle, which is fundamentally important to what we do in the future when we start talking about probability. And it says the following. It says if n operations are performed in order, so this could be anything from choosing things to flipping a coin n times. We're doing something n times, or we're performing n operations in order, and the number of possible outcomes for each operation are n1, n2, out to n sub n respectively. So you're performing these operations. Each operation has a number of possible outcomes. And so for the first operation, you've got n sub 1 different possible outcomes. For the second operation, you've got n sub 2 different outcomes, and so on. Then if you want the total possible combined, the number of total possible combined outcomes, all you have to do is multiply them all together. Alright, so I had n1 possibilities for the first event, I had n2 possibilities for the second event, I had n sub n possibilities for the last event. Well, if you want the total possible combined outcomes, multiply them all together. And I think this is best explained with an example, so let's just jump straight into examples here. Here's our first example. We've got a new car model, comes with 5 choices of color, 3 choices of transmission, 4 choices, 4 different types of interior, and 2 choices are 2 different types of engine. So the question is, how many different variations of this model are possible? And here we're going to invoke the multiplication principle. So I've essentially got 4 different events, right? I've got my first event is I'm choosing the color. So I choose my color. My second event is I come in and I choose my transmission. My third event is I come in and I choose my interior. And lastly, my fourth event is I choose my engine. Okay, so you choose your color. You've got 5 choices there, so there's 5 different possibilities, right? 5 different possible outcomes, so there's 5 different possible choices for the color. For the transmission, I've got 3 choices for transmission. For interior, I choose my interior, there's 4 different possible outcomes here. And lastly, choose my engine, there's 2 different possible choices here. So the multiplication principle says the total number of possible outcomes from 4 events with 5 possibilities for the first event, 3 possibilities for the second, 4 for the third, and 2 possibilities for the last one. The multiplication principle says if you want the total number of possible outcomes, all you have to do is multiply them all together. So the number of different variations is, all I have to do is multiply this together. It's going to be 5 times 3 times 4 times 2. Which is what? 5 times 2 is 10, times 12 is 120 different variations. Alright, so this is how the multiplication principle works, is you have a certain number of events, and this is how I like to think of it in my mind. I've got my first event, I just put a line, and I indicate how many choices I have there. Second event, I put another line, I fill in how many choices I have there, 3 in this case, and then 4, and then my last event is 2, and you just multiply them all together. So we'll do this again on another example. Here's another problem. How many 3-letter code words? And I'm saying code words because I don't mean we're not constructing real words here, just combinations of letters. How many 3-letter code words are possible using the first 8 letters of the alphabet? So once again, I'll set this up like I did last time. I'm making 3 choices, right? I'm making a choice. I've got my first letter, my second letter, and my third letter. So I've got 3 different events. For the first event, I have to choose a letter. How many letters am I choosing from? I'm choosing from a pool of 8. So I have 8 possible choices, or 8 possible outcomes there. Second letter I choose. There's no restrictions on this, so second time I choose a letter. I've got 8 possible choices. And my third event, I choose a third letter. I have 8 possible choices. So my total number of possible words, code words, is given by multiplying all of these together. So the answer would be 8 times 8, oops, can't write, times 8, which I believe is 512. 2 cubed, yeah, that's right. Okay, so I have 3 events, 8 choices for each event, so the total number of possible outcomes is the product of 8 times 8 times 8. Let's do something a little bit more exciting. How about if no 2 letters can be repeated? Oh, I don't know why I have 2 letters there. How about if no letter can be repeated? So what now? Once again, I'm making 3 choices, 3 events, first letter, second letter, third letter. For my first event, I just choose a letter, right? I haven't repeated anything yet, so I just choose a letter. I have 8 choices here. But now when I'm choosing my second letter, how many choices do I have now? How many possible outcomes now? Well, I've already put a letter here, and I'm not allowed to repeat it. So whatever that letter is, I have to remove it from my pool. Now I only have 7 choices. Right, now I only have 7 choices of letters left. And now for my third choice, I'm choosing one of these 8 letters, but once again, I've already used 2 of them, meaning I'm left with 6 letters that I can choose from. So for my third choice, I've got 6 possible outcomes here. So how many different total possible outcomes? Well, once again, you multiply them all together, but now it's 8 times 7 times 6, and this is 336. This is really important to understand, right? It's really important to understand why this is 8, 7, and 6. It's because I can't repeat letters, so I can choose anything for the first letter, but now I only have 7 letters to choose from because I can't repeat the first one. And for my third choice, I've already used 2 letters, so I only have 6 letters to choose from here. Let's do one more. How about C? If no adjacent letters can be the same. If no adjacent letters can be the same. Alright, so once again, 3 choices of letters. First letter, well, I'm not restricted by any of this adjacency stuff because there's nothing adjacent to it yet. So my first letter, I can choose any of my 8 letters. Second letter, I come in, I have this event, I choose a letter, and once again, it cannot be the same as the letter that's adjacent to. So that letter there is ruled out, meaning I have 7 possible choices here. Any of the 7 letters that are not the same as this one. And then for my third choice, well, doesn't matter what this letter was, right? Because it's not adjacent to it. So this can be any letter except whatever this one was, meaning I once again have 7 choices there. So in this case, our total possible outcomes is 8 times 7 times 7, which is 392 possible choices. So we'll stop here. We won't do too many examples of this. You'll see more for homework. You'll see more in the text if you want to see more examples. But this process is very important to understand, this multiplication process. And I highly recommend thinking of it like this. I highly recommend for each choice, just put a little line, and then above that line, indicate how many choices you have for that event, and then how many choices you have for the next event, and then how many choices you have for the next event. And then multiply them all together to get the total number of possible outcomes. Thank you.